In the previous video, I explained this problem and all of the details of it, so I won't do that again here. But here we're going to solve the problem in a different way. And in this time, we're going to solve the problem using the conservation of energy method. This problem has a lot of parallels with the work energy method, but it is different, and so it's really important to notice the subtle differences. First of all, you can't have any non-conservative forces. So the only reason we're allowed to use this method is because we have no friction and with no external forces. So that's why we're allowed to use the method here. The formula for conservation of energy method is T1 plus V1 is equal to T2 plus V2. What this is saying is that the kinetic energy 1, which is T, plus the potential energy 1, which is V, is equal to the kinetic energy at the second moment and the potential energy at that second moment. In this problem, because the system starts from rest, our T1 is equal to 0. We have no kinetic energy. None of the blocks have a velocity at the first moment, so there's no kinetic energy. But we do have potential energy at both moments and kinetic energy. For this problem, you have to set datums because potential energy has to be relative to something. So for this problem, I'm going to set my datum for block B. I'm going to set it here for the potential energy. And I'm going to say that the block, and we know already that B moves up by 1 meter. So the next position of block B will be here, and our delta XB is equal to 1 meter. So that's a positive number from the datum. It's moving upwards positive. Note that the datums for potential energy are completely separate from the datums that we used for the constraint equations. And so in this case, this datum here is really just in reference to potential energy that's separate from the constraint equations. For block A, I'm going to draw the datum. I'm actually going to draw the datum to be kind of here where A is starting. And then I'll be able to define block A is moving down this way. So the HA, if I draw that as a separate triangle here, we know that it goes down 2/3 of a meter. And then here, the HA for the potential energy of A, here our HA will be equal to 2/3 sine of 20 degrees, which is equal to 0.28 meters, because this is 20 degrees here. So from here, we set the positive, we set the datum for A there, and downwards here means that the potential energy of A is actually going to be a negative number. So let's plug this into our equation now. So we know the potential energy at point V1. So here I'm going to rewrite this equation. The T1's already 0, so 0 plus the potential energy, and here we're looking at the entire system at once. So here we have V1 is equal to the potential energy of block B at that initial moment. That's equal to 0 because the potential energy of block B at the first moment, it's at the datum. So it doesn't have potential energy relative to that point. And then here for block A, it's also starting at its datum, so its potential energy is also equal to 0. So this means here, this was our T1 equal to 0, and our V1 is equal to 0. That's going to be equal to our T2, so the kinetic energy at the second moment is going to be 1/2 ma VA squared plus the kinetic energy of the block B at that point, VB squared. This is our T2, and this will be plus our potential energy. So now the potential energy from block B is here, so block B has moved upwards from its datum, so it has gained potential energy. So this will be plus MB times G, so the weight of B, times our delta X B, minus, because here the potential energy of A is below this datum that we set, so it will be minus MAG times that HA that we determined. These terms here are our V2, that's the potential energy at our second moment. Now in this equation, for V2, we know all our values. We know our delta XB and our HA. The two unknowns that we have are here, VA and VB. Now we can use the same constraint equation as before, and you'll see that 29 VA squared minus 10.99 is equal to 0. And our VA is equal to 0.615 meters per second down the slope. Our VB comes out the same as negative 0.92 meters per second, which means our VB is 0.92 meters per second upwards. So in this case, our results are exactly in agreement with the principle of work and energy. So I just want to highlight something here. In the conservation of energy method, we did use the same constraint equation, so that didn't change. The system itself isn't different. So the relationship between the position of A and B and the velocity of A and B, those remained the same, so we still use the constraint equation. But what was fundamentally different here is that in terms of the force due to gravity, we considered that here in the potential energy. So we didn't consider that force from gravity as a force. We considered it as a change in potential energy, and the same thing with kinetic energy. And so we didn't do the same type of force balance. And that's really fundamentally one of the main differences between the two methods. If you don't have friction or external forces, you'll find that the conservation of energy method is a little bit easier, it's a little bit faster. But if you're not sure, then the work energy method is a safer bet because it will capture those forces. So if you're not sure, I would say default to the work energy principle, but conservation of energy is a shortcut.